Hello. How much evidence, at most, does a given p-value provide for the alternative hypothesis over the null hypothesis from a Bayesian point of view? Now, some people might think that a p-value of 5% would be something like 20 to 1 evidence in favor of the alternative hypothesis over the null hypothesis. But that is definitely not the case. In fact, p-values are generally a lot weaker than you might think. And we're going to talk about this. For this video, I am going to use a concrete example. So let's go ahead and set up that example. So first thing, we're going to need a sample model. We are going to need a family of distributions for the observations. Now, we're going to have one of these distributions for each possible value of theta between 0 and 1. So what we're going to do is we're going to flip a coin 200 times, and we're just going to count how many heads we get. Now, this is going to be the probability of getting k number of heads out of the 200 coin flips, given that the probability of getting heads on any given flip is theta. So for example, if theta is 1 over 2, that means 50% heads, 50% tails. If theta is 0.8, that means 80% heads, 20% tails. And we are going to assume that all the flips are, independent and identically distributed. So p of k given theta is just going to be this, which is just going to be a binomial distribution. And the last bit of setup is going to be that we are going to be making a claim. So we have a null hypothesis, which will state that theta is equal to 1 over 2, that the coin is a fair coin, and the alternative hypothesis will state that theta is not equal to 1 over 2, that it could be anything else between 0 and 1. And it is going to be intentional that for our null hypothesis, we are choosing something called a point null. It says that the parameter has a specific value. If we weren't doing this, if we said that for the null hypothesis that the parameter could have multiple different possible values, then our analysis would have to look a little bit different, but we're going to go with the point null. This is a very common situation in frequentist statistics. In this part of the video, I'm just going to review a little bit what the whole idea here is of testing the null hypothesis and what the p-value is. So here I have a probability distribution. This is going to be the probability distribution for the number of heads that we will observe, assuming the null hypothesis is true, assuming the coin is fair. So you see that 100 heads is going to be the most likely outcome, and 200 heads or 0 heads, those are going to be the least likely outcomes. So let's say we get 150 heads out of our 200 coin flips. What would the p-value be in that case? Well, 150 heads is right here, and we see that the probability of getting 150 heads is less than the probability of getting 100 heads. That means that getting 150 heads is a more extreme result than getting 100 heads. In fact, this is not drawn to scale. This should be way, 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 way lower than it actually is, but that's okay. It's just an illustration, conceptual illustration, right? Now, an equally extreme outcome would be to get 50 heads. Getting the probability of getting 150 heads is exactly equal to the probability of getting 50 heads. This thing is symmetrical about the 100 vertical line right here. Now, an even more extreme result than 150 heads would be 151 heads or 49 heads. An even more extreme result would be 152 heads or 48 heads. The p-value associated with getting 150 heads is the probability of getting a result as extreme as 150 heads or more extreme, assuming that the null hypothesis is true. In this particular case, the p-value would be less than 1 in a trillion. It's like a super small p-value. So the smaller the p-value, the more surprising your data is, assuming the null hypothesis is true. It's sort of like a measurement of the discrepancy between your data and the null hypothesis. Like, how far away is it between your data and the null hypothesis, so to speak. Here is just a little bit more of a mathy way of explaining the previous slide. So this is little p, this is big P. So little p for p-value, the p-value associated with getting k number of heads is just going to be the sum of the probabilities of getting I number of heads for all the possible I number of heads that you could get, where they are at least as extreme as getting k number of heads. That is, where their probability is less than or equal to the probability of getting k number of heads. All of this assuming that the null hypothesis is true, which is what this given 1 over 2 means. It means given that the heads rate is 50%, which is the null hypothesis. And the way that p-values are interpreted in frequent statistics is that the smaller the p-value is, the more evidence you have in favor of the alternative hypothesis. Although it is important to point out that the smaller the, it does not deductively, you cannot deductively say that the smaller the p-value is, the more probable the alternative hypothesis is. That is, that would not be correct. Let's continue with our concrete example. So we are going to assume that we got an observation of 115 heads and 85 tails out of our 200 coin flips. And the question is going to be, first of all, what is the p-value associated with this? What other observations would give rise to the same p-value? And the question is going to be, at most, how much does this observation favor the alternative hypothesis over the null hypothesis from a Bayesian point of view? And another question is going to be, if we don't think about the observation itself, but just the p-value associated with it. Say someone told you what the p-value result of the experiment was, how much at most would that favor the alternative hypothesis over the null hypothesis from a Bayesian point of view? The p-value associated with getting 115 heads is going to be this very particular number, which I will refer to as little a. It's about 4%. And there is one other observation that gives exactly this same p-value, little a, which would be if we observed 85 heads. So in either of these cases, we get a p-value of about 4%. All right, here I've got model 1, I've got model 2, and I've got some data. So I'm going to say that model 2 is 10 times more probable than model 1 in the absence of my data, right? This is the prior probabilities, and this thing is called the prior odds of model 1 to model 2. But now, let's think about my data. Right, what's the probability of getting the data I've gotten if model 1 is true, and what's the probability of getting the data that I've gotten if model 2 is true? Well, it's twice as likely to get the data that I've gotten under model 1 as it is under model 2. What that means is that model 1 explains my data better than model 2 does, in a 2-to-1 ratio. Now this thing is called the Bayes factor. So what I'm going to do is I'm going to multiply my prior odds by the Bayes factor. So prior, I like model 2 10 times more than model 1. But the data likes model 1 2 times better than model 2. So when I multiply these together, I get 1 over 5, which means I'm going to like model 2 5 times more than model 1, so to speak. This is the posterior odds. It's the probability of getting model 1 given our data divided by the probability of getting model 2 given our data. So maybe model 1 says it's going to rain in a week, and model 2 says it's going to be sunny in a week. And I'd say, you know what, I really think it's going to be sunny in a week. That's 10 times more probable than that it's going to be raining in a week. But I do go outside and I see that it's cloudy outside, and I say, okay, it would be cloudy. The probability that it would be cloudy outside is 2 times greater under model 1, the model that predicts it'll be raining in a week, than it is under model 2, the model that predicts that it will be sunny in a week. So I multiply those, right, Bayes factor times prior odds, and I say, okay, you know what, I still think it's going to be sunny in a week. I still think model 2, the one that predicts it's going to be sunny in a week, is more probable than model 1, but no longer 10 times more probable, now just 5 times more probable because of this Bayes factor, because of this data, right? The Bayes factor, it points in the direction. It tells you what direction the data points in and how strong, and in this case it's pointing in the direction of favoring model 1 over model 2, and sort of with a strength of 2 over 1, right? 1 over 1 would be that it doesn't point in either direction. 1 over 1 would be that it favors the models equally, in which case if it favored the models equally, I wouldn't need to change my prior odds at all. I would just be multiplying by 1. So that's how that works. And we're going to be interested in this Bayes factor and putting a bound on it. If we get 115 heads, that is associated with a p-value of about 4%. It was the particular value I referred to as little a. From now on, I'll just call it 4%. Now, there's 2 ways to get a p-value of 4%. One is to get 115 heads, and the other is to get 85 heads. So we're going to calculate another minimum Bayes factor. The top is going to represent the probability of getting a p-value of 4% if the null hypothesis is true. And the bottom is going to refer to the probability of getting a p-value of 4% if the best possible version of the alternative hypothesis is true. That is, the version of the alternative hypothesis that maximizes the probability of getting a p-value of 4%. Hey, I just want to explain this ratio again, since I snipped some things out of the video. So the probability on the top is the probability of getting the p-value that we got if the null hypothesis is true. The probability on the bottom is the highest possible probability of getting the p-value we got if the alternative hypothesis is true. Technically, the least upper bound. Now, we don't know which version of the alternative hypothesis is true, assuming the alternative hypothesis is true. So what this ratio represents is how much do we favor the best possible version of the alternative hypothesis over the null hypothesis based purely on the data that we got. And you would multiply that with the prior odds in order to get the posterior odds. Now I'll let my prior worm segment finish off the video for you. And we get this ratio, which gives us a minimum Bayes factor of 0.208 ... Now if we invert this, we get about 4.78. Now remember, in the beginning, the misconception that one might have is that a p-value of 5% would mean that the evidence points in favor of the alternative hypothesis over the null hypothesis by a ratio of about 20-1. So for a p-value of 4%, that would be more like a ratio of 25-1. And what this says is that in the best case scenario for favoring the alternative over the null in terms of the data, it should be a ratio of 4.78-1, not 25-1. And in fact, assuming if you were to get a p-value of 4% in this particular situation, and you were to interpret that as, the data pointing to the alternative over the null in a ratio of 4.78-1, that would be pretty unreasonable, probably. That would be pretty extreme, because this is an upper bound. This is a pretty extreme upper bound. In most, typical situations, it wouldn't be anywhere near this large. In fact, if you assume that under the alternative hypothesis that there's a uniform distribution for theta between 0 and 1, that it's sort of equally likely to be anywhere between 0 and 1, then getting a p-value of 4% wouldn't just fall short of this number here, it would actually favor the null hypothesis over the alternative hypothesis. You would actually be even if you were like, if you started out favoring the null hypothesis over the alternative hypothesis and then you got a p-value of 4%, if you think under the alternative that theta would be uniformly distributed between 0 and 1, that nothing is more likely than anything else between 0 and 1 under the alternative for theta, you would actually, after seeing that 4% p-value, you would be even more confident in the null hypothesis as a result. That 4% would actually be interpreted as helping you to confirm the null hypothesis, as surprising as that might sound. So yeah, and by the way, this is a maximum Bayes factor of 4.78 for this particular concrete example I went over. But every problem, depending on what the problem is and what assumptions you make, you would get a different maximum Bayes factor. And in fact, this one is pretty large compared to some of the ones that I've commonly seen. So it's already, even for a maximum Bayes factor, it's already pretty large. It's pretty atypically large. So yeah, if you have any questions or comments, I would love to hear them. Thank you for taking an interest in this and for sticking through some statistics stuff. Yeah, I hope you have a good day. Take care.